Today, on how it's made. Retractable ballpoint pens. Solar salt. And Tubas. The ballpoint pen was designed as the answer to the fountain pen's many annoyances. The hassle of having to manually refill the barrel with ink that dried slowly and often smudged. The ballpoint has a tiny steel ball in its tip, which applies quick-drying ink from a ready-made cartridge. When the ink cartridge inside these retractable pens runs out, you simply replace it with a new one. Working from the initial design, the pen factory makes molds for all the pen's plastic components. The injection molder first shoots hot liquid plastic into molds for the barrel's rigid core, then into other molds for its soft rubber grip. The tubes for the ink cartridges are also made of plastic. Machinery aligns them in the same direction, then prints on the company name, model number, and tip size. Here, a filling machine injects 0.8 grams of ink through the tip. To prevent the ink from evaporating, it plugs the other end with 0.1 grams of silicone paste. Meanwhile, high-precision machines progressively shape the pen's tip out of stainless steel blanks. The equipment drills a 1 millimeter channel through the blank, then, in quick succession, fashions the tip into a cone, cuts 5 tiny ink flow channels into the ball socket, and seats a 1 millimeter diameter stainless steel ball in the center. Another machine then inserts a finished tip in each ink-filled tube. A scanner then checks the length and the ball of each cartridge. This magnification shows the width of the 5 ink flow channels next to a human hair. Random samples undergo an air pressure test to check the ball's position and movement. Anything less than perfect will clog the pen. They close off the end of the cartridge with a plastic cap. The cartridges now go into a centrifuge, which forces the ink to the tip, eliminating any air bubbles that would obstruct ink flow. Every cartridge passes through this writing test machine. That blue light is a sensor, which triggers the machine to reject any defective cartridge. The components now come together in the assembly department. The machine assembles the clip, sleeve, and barrel. The clip is made of chrome-plated spring steel, a strong metal that regains its shape when flexed. The machine then flips the assembly over to receive the internal components. First, the pen's 2-part push-button mechanism. Part 1, the plastic push-button. Part 2, a device called a rotor. With each click, it rotates the refill 45 degrees, so the tip wears evenly. The ink cartridge goes in tip side up, the plug on the back fitting into the rotor. This device forces spring steel wire through a coiling block. This produces a tiny spring that provides resistance to the push-button mechanism. A grabber places the spring over the cartridge tip. Now they close up the pen by adjoining the barrel's bottom part. The machine screws the 2 parts together to a specific tightness. The final assembly machine tests the push-button mechanism to ensure it retracts the tip properly. This also prepares the pens for packaging, as they go into the boxes with tips retracted. The factory subjects random samples to endurance testing. This device clicks the push button 100,000 times. Only then does a printer put the logo on the barrel. This company's engineering of its ink flow channels and tip delivers, on average, 4 kilometers of writing per cartridge. Salt comes from 3 sources: salt mines, land that was once a seabed, and from oceans and saltwater lakes. Factories extract salt from water by evaporation, either mechanically or naturally, by letting the sun work its magic and produce what's called solar salt. This large hunk of salt crystals comes from Great Salt Lake in the U.S. state of Utah. At full water level, the lake is 7 times saltier than the ocean. Harvesters scoop up salt from shallow crystallization ponds and load it into trucks. It's the end result of a 2-year evaporation cycle, which has seen the lake water, called brine, slowly give off its moisture in a series of concentrating ponds. What remains is a bed of salt crystals about 30 centimeters deep. The truck dumps its cargo onto the factory's conveyor system. First stop is a rinsing station to remove contaminants such as algae and dust. Using fresh water would dissolve the salt, so they flush the crystals with lake brine. Next, hot air dryers remove the moisture and salt dust within about 3.5 minutes. The salt crystals then roll across a series of sorting screens with progressively smaller openings. This classifies the salt crystals into 3 grades: coarse, medium, and fine. Each grade goes onto a separate conveyor that transports it to a designated storage bin. The factory uses medium-grade salt to make pellets for water softening equipment. This press compresses the crystals into pellet shapes, along with certain additives to help the water softening equipment perform better. Some municipal water supplies have a high mineral content. This hard water makes soap difficult to lather and leaves stains on sinks, bathtubs, and toilets. Salt triggers a chemical reaction that dissolves the problem minerals. The factory packages water-softening solar salt in bags as well. It also produces a variety of other solar salt products, such as swimming pool salt, road salt for melting ice in the winter, and of course, culinary salt. The factory's automated packaging equipment fills both paper and plastic bags. This company also sells solar salt to several industries for use as an ingredient in products such as detergent. There's also the agricultural market. Farmers buy blocks of solar salt, plain or enriched with minerals, as a nutrient for their cattle. The factory produces different salt and mineral formulations, each dyed a different color for easy identification. To produce salt for cattle, the machinery drops 23 kilograms at a time into a block-shaped mold. A press applies 750 tons of pressure, bonding the crystals into a block. The farmer simply sets out blocks among the cattle, and the animals lick away to get their dose of sodium. A label identifies the type of salt block. This one contains iodine to prevent a thyroid disorder called goiter. A tasty and therapeutic bovine snack, courtesy of a saltwater lake and sunshine. The tuba is the largest instrument in the brass family and the one with the lowest pitch. Famous orchestral composers from Stravinsky to Gershwin have included significant parts for tuba in some of their best-known works. Some composers have even written full concertos for tuba. Tubas are made of brass, sometimes silver or gold-plated. The instrument consists of valves and tubing, ending in a flared bell. The bell flare begins as a brass disc 55 centimeters in diameter. They use a range of tools and various mandrels to work the brass into a preliminary bell flare shape. They use sandpaper to remove any marks left by the tools. Then cut a hole in the center. To make the conical tail that leads to the bell flare, they bend and hammer a thin brass sheet around a tail-shaped mandrel. To To join the seam, they cut notches along one edge, then hammer them over the other edge. The artisan then melts filler metal over the seam with a high-temperature gas torch, a process known as brazing. Then they use a wooden mallet to round out the shape. They use a pressure roller to flatten out the mallet dents and further refine the surface. After notching the wider end of the tail, they assemble it to the bell flare. They dab on flux, a chemical that prepares the surface for brazing, then tack the parts together. They hammer down the notches and braze the seam all around. This assembly, now called the bell, goes back on the lathe. Using a belt sander, they flatten all the seams flush with the surface. On another mandrel, with lubricant assisting the process, they finalize the bell's shape. Now they trim the edge to the correct diameter. Bend it back a bit. Polish the perimeter with a sanding head, then use a special tool to roll the edge over itself. This forms what's called the bell bead, a lip that reinforces the bell and gives this end of the instrument a finished look. A computer-guided engraving machine puts the company logo and model number on the bell. Each of the Tubas' 100 or so tubes must be bent into a specific shape. The first step is to fill them with hot liquid pitch, which hardens as it cools. This keeps the tubes from collapsing as they're bent. After bending, the tubes go into an oven to melt out the pitch. Certain bent tubes are enlarged in a machine called a hydraulic blowout press. It pumps oil into it at high pressure. This blows the tube walls outward against the die, forcing it to assume the new shape. Certain bent tubes are conical, others cylindrical. The cylindrical ones go through what's called a ball-out operation. This machine forces steel balls of the proper diameter through the tube. This enlarges any spots that are too narrow. Before bending, certain tubes have to go through a drawing machine for resizing. With lubricant easing the way, it draws the tube between an inner mandrel and an outer washer. This forms the tube to the correct diameter and wall thickness, while also stretching it lengthwise. Coming up next, we'll see where this tube fits in the finished instrument. Tubas come in different versions. A B-flat tuba, for example, is nearly 5.5 meters long, whereas an F tuba is about 3.5 meters long. Tubas have anywhere from 3 to 6 valves. Pressing different valve combinations produces different notes. To build the valve section, they insert parts called knuckles into the valve cases. Spacers hold the valve cases the proper distance apart, while this alignment plate positions the cases in the correct configuration. Next, they insert connectors to later link the valve section to the rest of the instrument. After brazing the parts together, they run a cutter through the valve cases to hollow them out. Here, you can see what the case interiors look like before cutting and after. Now they begin soldering on the valve section's tubing, working from the valve cases outward. The tuba's frame section is made up of several U-shaped parts. Workers assemble them with connecting rings. They insert a support brace inside this frame piece. Then position tabs onto which they'll later mount the valve section. They clamp the tabs in place, then solder them on. Then they attach the bell section to the frame. Before adding the valve section, they give a preliminary buffing to what they've assembled so far. They brush some liquid polishing compound into the places that they couldn't access with the wheel, and buff those areas with a rag. Then a final overall buffing, until the brass reflects like a mirror. Meanwhile, the valve section assembly continues. First, they close off the bottom of each valve case with a screw-on cap. Then drop in a spring to provide resistance for the valve piston. Then the piston. A felt to cushion it, a top cap, another cushioning felt, and finally the finger button. A little oil ensures all the buttons move smoothly. The felts inside prevent the pistons from making a clanging sound as they move up and down. Now for the Tubas tuning slides. A coat of grease helps them move in and out to increase or decrease the overall length of the tubing. Shortening tunes the instrument higher. Lengthening tunes it lower. Now they screw the finished valve section to the assembled frame and bell sections and insert the main tuning slide. Finally, the Tubas mouth pipe, made not of brass like the rest, but of nickel silver. They spray the entire instrument with cleaning solution to remove any grease residue and fingerprints. Prior to assembly, each section was cleaned and coated with a clear lacquer to ensure the tuba will always look as good as it sounds.